Hello Suraj, can you please turn off your mic? So, am I audible? Hello? Am I audible? Suraj, am I audible? Suraj? Hello? Hello? Are you there, Suraj? Am I audible to you? Am I audible? Hello? Newton, can you reply like, am I audible? And if my screen is visible? Hello? Can anyone confirm, am I audible? Am I audible? Okay, is the screen visible to everyone? Okay, I think we'll wait for 2-3 minutes and maybe someone else may join, and we'll be starting in today's session in 1-2 minutes or 2-3 minutes. Okay, I think we can start today's session. I welcome you all to the week 6 of the problem solving session. Like, this is our sixth session of the problem solving for the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya from IIT Roorkee. My name is Adnan Farooq Khan and I am PhD research scholar at IIT Delhi. And like you know, I take this problem solving session on every Tuesday from 7 to 9. And like always, I'll be first briefly going through what has been taught in this week, and then we'll be moving towards some of the problems that will be solved in this session, which will help you in solving your weekly assignments or problems that have been given to you. So coming to this week, week 6, what has been taught to you is, I mean, the topics that have been taught to you are like voltage and current source inverters, pulse width modulated inverters, and multi-level inverters, and lastly like Z source inverter. So I'll be briefly like giving you the overview what has been taught to you about these, like briefly. Then we can move towards the problem solving session. So that this is only to brush up. This revision is like to brush up the ideas and the concepts which will help you in solving the questions. So firstly, like we'll be sorry, just a minute. I'll change its position a bit. Or we can have it like here and see. So like the different types of inverters like that have been discussed in this week were voltage source inverters and current source inverters. Then that what has been taught is like PWM inverters and subsequently multi-level and Z source inverters. Firstly we'll be starting with the voltage source inverter, which has been mostly used. Like you can see here, what do you mean by the inverter? Like we inverter is like a, you can see a converter, voltage source converter, which converts like our, if we are having a DC and we want an AC from this DC, and the converter that has been used for this DC to AC conversion, we call them as inverters. What we have here, you can see, is a constant VDC voltage. Like you can see in this figure, we have a constant VDC voltage, and what we want to have achieve like at the output, let us say there is a load that is connected, sorry, like keep it here. If you can see, let there be a load that is connected between this A point and N point, and we have these terminals A and N terminals, and we are having like a constant DC voltage that is given to us. And what we have is a one leg of switches, like we have S1 and S2 switches, and you can see the S1 is connected to the positive rail or terminal of this DC voltage source, and you can see, and the bottom terminal of this S2 is connected to the neutral point, or you can see the negative terminal of this DC rail. And what we can see, and we have a point A that is the midpoint of this S1 and S2. Like we have these two switches, and the midpoint of these switches we have a connection like from this point A, and we will see what if we are having any load, or like we can see between this A and N points, can we have like a AC voltage or voltage across these BAN points. From this, can we achieve this from a constant VDC source? So what we have here is a constant VDC source, and we have two switches that are connected like in series, and we have a point like midpoint between them as A. So one thing you can see here is like we have two switches we cannot, we know that we voltage source cannot be shorted. So what we mean by that is, like, we cannot turn on this S1 and S2 simultaneously. If we turn on this S1 and S2 simultaneously, we will be shorting this DC source. And like, if we short the voltage source, like a tremendous amount of current can flow, and which can damage this source as well as these switches. So one thing, in case of voltage source inverters, we need to have, like, we cannot short the source. And so we have two options with us, like, we can either turn on S1, and at that moment we have to turn off S2, and when we will be turning on S2, at that moment we have to turn off S1. So you can say, like, we have to switch on these S1 and S2 in a complementary fashion. That means when one device is conducting, other needs to be turned off. So now we have this VDC voltage that is with us, and we have this switching network. Now let us consider what will happen if I turn on this S1 and this S2 is turned off. So when this S1 is turned on, you can see that this point P will be connected to point A. The point P which is connected to the positive rail, the point P which is connected to the top of this switch and is connected to the positive rail of this DC bus here. When this S1 is turned on, you can say that this point P will be come across this A. And if you can say, when this is positive terminal here, and you can see the voltage that will be between A and N will be equal to VDC. So if we turn on S1, the voltage, the VAN voltage across this VA and N point here will be VDC. So when the S1 is turned on, we'll be having VDC voltage. So now we will see, if we turn off this S1 and turn on this S2, you can see when we turn on this S2, you get it? Like, I'll show you this. When we turn on this S2 and S1 is turned off, you can see this point A will be connected to this point N. You can say that the voltage across this VAN will be equal to 0. Are you getting? So that is what has been put up in this table. Like, VAN is the voltage that will be getting across this VAN, and when S1 will turn on and S2 will be off, we'll be getting VDC voltage across this VAN. And when this S1 will be off and S2 will be on, we'll be getting a 0 voltage. So you can see here, like, because of that, due to this one leg and a DC source, we are able to achieve like two levels of this voltage, VDC and 0. We'll be having a VDC certain amount of time when S1 is turned on, and we'll be having the 0 voltage when S2 is turned off. Like, we got a pulsating voltage, but it is unidirectional, that it has a positive of we got a 0 and positive value. Now we'll be subsequently see how we'll be able to generate this minus VDC as well, so that, like, we can have positive and positive VDC and negative VDC, so that we can have like a square wave kind of a AC voltage. This was, now if we can move, this was about the voltage source converter. Now we'll be coming towards this plus VDC and minus VDC, how that is generated. But before that, like, we'll be seeing, like we saw about this voltage source inverter, we'll be seeing the topology about this current source inverter. So this, in a similar fashion of the voltage source inverter, we have a current source inverter, where our source is a current source. Like, our current source, where our source is a current source, and we have this switching network, like one leg of switches with S1 and S2, where S1 is connected to the P point and S2 is connected, bottom of this S2 is connected to the N point. We can say that this current source like can be achieved by having a voltage source with a high inductance in series with that. What will happen with due to that inductance, it won't allow any change in the current. Like we can assume that this source is a constant current source at that moment. So here we have assumed like this is a constant current source where current can have only one direction. What happens, like what we saw in the voltage source inverters, is we cannot like turn on both the switches simultaneously. What would have happened at that time is like we would have shorted the source, like source would have gone shorted, and that would have been detrimental for our converter. In a similar way, we have like, since this is a constant current source, if we turn on S1 and S2 simultaneously, like that is possible in this topology, because like if S1 and S2 are simultaneously turned on, like we can have like current can flow through the S1 and S2 and back to the source, like it will have a path. But what we have to keep in mind that in current source, our current should not get interrupted. That means we cannot have a condition, that means where S1 and S2 are both off. Like I told you, like this current source may be of, we have a DC voltage source and with a large inductance in series with that. What would happen, like when we have interrupted the current through the inductor, there will be a large di by dt which would result in a large voltage which can damage our source as well as these devices. So what we have to keep in mind is that in the voltage source inverters we cannot short the source and in the current source inverters we cannot leave the current source open. That means S1 and S2 cannot be off at the same time. So in a similar, now we will see when can we get the positive current and the negative current. Let us see here, when we have S1 on and S2 is off, the current through the VAN or the load will be IA. Let this current be IA. This will be equal to IDC. If we connect a load between this point A and N, we can say this current IA will be equal to IDC when this S1 is turned on. And if we turn off this S1, sorry, here's a mistake. So the other condition is like this: when this S1 is on and S2 is on here, so the current will flow through S1 S2 and back to the source, and there will be no current through this A terminal. That will be when S1 and S2 are on, the source current will flow freewheel through this path and IA will be equal to 0. So here we saw that when S1 is on and S2 is off, we get a positive current. When S1 and S2 are off, S1 and S2 are on, we get zero current. This was about current source inverters. Now we will see, if we are having a single phase inverter, how can we get a single phase AC from this constant VDC voltage. This is the circuit topology for a single phase voltage source inverter, where we have a DC, and like we saw, we have one leg with S1 and S4 switches, other leg is S3 and S2 switches, and the load is connected between point A and point B. So this load can be anything, like a resistive load, inductive load, RL load, or RLE load, whatever you want to say. You can see the point P is connected, S1 and S3 is connected to the point P, and bottom of this S2 and S4 is connected to the point N. And previously what we saw is, like, because of this one leg S1 and S4, we were able to achieve 0 and VDC voltage. Now we will see. And if we want to have now we want to have like VAB voltage, that will be equal to VAN minus VBN, that will be equal to VAB. If we know VAN, we know VBN, we can have VAB voltage. That you might have seen how the derivation is done during the course lectures. So now we'll see how these like voltages will get generated. Now in this kind of a generator, like when we can have a unipolar or a bipolar modulation. Now we can see here unipolar means like at one moment of time only, like we can get 0 to VDC, and for some time we will get minus 0 to minus VDC. You would have like we can I will talk about that in PWM. Now what we want to have, like we want to have the positive voltage across this load VAB. So if I turn on S1 and S2, you can see when S1 and S2 are turned on, you can see we can get like this point P will be at point A and B will be at N. So you can see the voltage across VAB will be equal to VDC. That is what you see here. When S1 and S2 are turned on, VAB will be equal to VDC here. And similarly, now this we were able to get due to this one leg, but now we wanted to have this negative voltage, so we can have an AC kind of a waveform which has a positive as well as the negative values, and here it is a kind of a square wave. So by switching on S1 and S2, we got to see that we were able to have plus VDC voltage. Now we will see what will happen when S3 and S4 are switched on. If you see, when S3 and S4 is switched on, you can see that this B point is connected to the positive rail of the DC bus or DC source. Like B point is connected to DC. Prior to this, when S1 was turned on, this A was connected to this positive of this DC source or DC bus. Now what is happening when we are turning off this S1 and S2 and turning on S3 and S4, B is being connected to the positive rail of the DC bus and A is being connected to the negative rail of the DC bus. So what that means, now if you can see, the VAB voltage will be equal to minus VDC. Because you saw that like the polarity of this VAB voltage is reversed, because positive now will be on the B and negative will be on A. Prior to that, A was positive and B was negative. That means like VAB will be now having minus VDC here. Now this was about the voltage, like voltage of what we will be able to generate this voltage. And if you can see, now we'll see about the current. Let this current be IO be the output current through this load, and depending upon this load, like we can have like a different shape of this current. If this is a resistive load, that it will be like a square kind of a thing. And also you can see like this may be the fundamental of that. Now if we are having a RL load, then we can have this kind of we can have like you will see it will like charge in this for this half and it will discharge for this half, and you can assume like maybe let this be the fundamental of the current, and let it be lagging by some angle theta here. This is only to emphasize on one thing, like this load current can be positive when the voltage is positive across this VAB. We can have a current that is positive for certain time and can be negative for the certain time. So what that means is like when the current is positive, it means it will be conducted like follow this path. When the current is negative, it will flow in the anti-parallel direction in the S1 and S2. What it would mean that our switches or devices in this topology like should be able to conduct the bidirectional current. That means these devices S1, S2, S3 and S4 should be able to conduct both positive as well as the negative current. So as you saw, like that has been reiterated in these 2 points, like to get this AC voltage like for plus VDC for one half and minus VDC for other half, what we do, we will be switching S1 and S2 together, and for the negative half we'll be switching S3 and S4 together. Also you saw like current can be in phase or be lagging by some amount. It can be like when the voltage is positive we can have the negative current as well as the positive current. So our devices should be able to have the bidirectional current carrying capability. Similarly, you can see in the negative, when the voltage is negative, we can have current that is positive as well as the negative. So in that interval as well, our devices should be able to have bidirectional current carrying capability. So you saw here like due to like this topology, if you can see, it resembles an edge. That's why we call it an edge bridge as well. So you can see due to this, like with the DC source and edge bridge, we are able to generate like a simplest of the ACs, like a plus VDC and a minus VC, that is kind of a square wave. You can see here, this is the simplest of the waveform that we could generate. Similar, like this was about the single phase. Now we will be moving towards like the three phase. What will happen in the three phase? So in the three phase, like we have two modes of conductions are there. Like one is 180-degree conduction mode and other is 120-degree conduction mode. As you can see, like as the name reiterates 180-degree conduction mode, this means like each device will conduct for an 180 degree. That means if one switching cycle corresponds to 360 degree, like the half TS by 2 will correspond to 180 degree. That means like each of these device will be conducting for 180 degree or pi interval. And you can see here in three phase VSI what we have three legs, which S1, S4, S3, S6, S5 and S2, and each of the midpoint of each is connected to a load. You can see this is the one arm of a load, this is another arm, and third arm, and the second arm terminal of the each leg is connected to a common point O, and you can say that this load is connected in the star fashion or Y, like this star, what we call a star connected load. This is a star connected load. So we saw like each of the leg will be able to generate 0 and plus 0 and VDC. So now we'll see how these devices will conduct. So what we saw here, like I told you, it is a 180-degree conduction mode. Just a minute. So you can say that this one S1 is when this S1 is conducting is for 180-degree, and when this S1 is turned off, S4 is turned on. You can see here S4 is represented by this gray one, and S1 is represented this by black one. So VAN will be equal to, when this S1 is on, VAN will be equal to, if you can see, VAN will be equal to VDC. VDC. VAN will be equal to VDC. And when this S4 is on, VAN will be equal to 0. In a similar fashion, we saw that I told you, like, each of these devices will be conducting for 180 degrees or pi interval. Like this interval is a pi interval, and what we'll do is here is like each and the pulses of each leg, that means this A leg, B leg and C leg, are shifted from one another by 120-degree. That is like a balanced three phase, where the three phases are shifted from one another by 120-degree. That is here, like this B, for B terminal, S3 will be turned on at the 120-degree interval, and it will conduct for 180 degrees, and after that it will be turned off and S6 will turn on. And in the here as well, we'll get VBN equal to VDC and 0, like due to this leg, individual leg, VBN will be equal to 0 and VDC. When S3 is turned on, we get a VDC, and when S6 is on, we get a 0. And you can this for the C leg, you can see here, when this similar to this, like S5 will start conducting at 240-degree from the initial point. That is, it is shifted from 240 from A phase, 120 from B phase, and in a similar fashion it will conduct for 180-degree and it will be off for 180-degree. These are like VAN voltages, and we can now calculate like VBN, like VAB voltage. That is, these are the phase voltage, like this is the line voltage. This is not a phase voltage, like this is the pole voltage, VAN. And you can see VAB line voltage we can calculate, that will be equal to, like you can see, it can be equal to VAN minus VBN. When we subtract this, like you can say, when here VAN S1 is on, here you can see the S1 is on. If you can see, like for each 60-degree interval, three switches are turned on. Like here S1 is turned on, and S6 is turned on, and S5 is turned on, here in this way. So if you can see VAB, like we have S1 is turned on and S6 is turned on, like this is the voltage. If you can follow this path, because here due to this it will be VA VDC voltage, and due to this will be 0 voltage. So overall, like between VAB will be having a VDC voltage, like if you follow this path, because here S1 and S6 are on. You can, if you follow the path S1, VAB and S6, VAB will be equal to VDC in this 60-degree interval. Now we will see for this 60-degree, other 60-degree interval. Here you can see S1 and S2 is on. So S2 is this. You are getting? So if you can see S1 No, for this interval also, like we have an S1 and S6 is on, then we will be getting VAB. Since we are calculating here VAB, like this will be corresponding, S2 will be corresponding when we are calculating VAC. So you can see here, if you can see, it is still connected to VAB. Through this it will have VDC up to this point. So we got this VADC. Now if you can see from this interval beyond 120 degree to 180 degree, S1 is on and S3 is on. When both S1 and S3 are on, we will be getting like VADC minus VDC will be getting the zero voltage here. You can see this will be like shorted here. You can see in this way. When S1 and S3 on, we'll be getting a zero voltage like this, because this will be DC VDC and this will be VDC, and difference of that will be equal 0. In a similar fashion, you can go in the negative side as well, and when you'll see that when we have S4 on and here we have S3 on, we'll be getting a minus VDC voltage from this. Here you can see that our line voltage is a Cauchy square wave and our pole voltage were square waves, and are this line voltage in the three-phase VSI in 180 degree conduction mode is a Cauchy square wave, and the off portion, like the zero portion, is for a 60 degree in the three-phase. Now also, like if you will be able to if you calculate what has been taught, the derivation of it, this RMS, like fundamental RMS of this VAB, like if you can calculate that, it will be like of this voltage using the Fourier analysis, it will be equal to 0.78 times VDC in the 180 degree conduction mode. The derivation of it I'll be not going into it because it has already been taught in the course and you can go through the lectures. Like this is only to brush up the ideas. Moving forward, like we have a 120 degree conduction mode. Like 180 degree conduction mode, here also you can get from the wording as well, like the title, like it's a 120 degree conduction. What would happen here, like each of the device will conduct for 120 degrees here. So we'll be seeing the waveforms here. You can see the S1 will conduct for 120 degree, then it will be turned off for 60 degrees, and after like 180 degree S4 will start conducting and it will also conduct for 120 degree. Got it? In a similar fashion, S3 and like B leg and C leg, they will be phase shifted from one another, phase shifted from like one another by 120 degree for the balanced three phase. And in a similar fashion, S3 will be turned on like a 120 degree, and S5 will be turned on 120 degree after that, or 240 degree from this S1. Here also you can see, like now we will be taking an interval from 0 to 60 degree. Here you can say that S1 and S1 and S6 is on, like this S1 and S6, like this line is starting from this, because it will repeat after that. So when S1 and S6 is on, we can get VAB, we know is equal to VAB will be equal to VDC when S1 and S6 is on. That is for this 0 to 60 degree. Now we will see for this 60 to 120 degree. Here you see we have S1 and S2 is on. S1 and S2 is on. So you see here VAC is equal to VDC. VAC is equal to VDC, and you can see that this point is floating, like this B is not connected, like this switch is also on, this switch is also on. We can say that whatever the potential be here will be here. because like this is a balanced hair, we can say that VAO will be equal to VOC will be equal to VDC by 2. So what we will be getting, V and O point will be equal to B point, like we'll be getting VAB will be equal to VDC by 2 here in this interval. In a similar fashion, you can see when S3 and this here will be getting minus VDC by 2, and then minus VDC when this S3 and when the S3 is on and S4 is on. So in the like 180-degree mode, like we got the line wave that was the form of a quasi square wave, but here we got at a step wave, like a where we have a VDC minus VDC, VDC by 2 minus VDC by 2, and VDC is a three-stepped wave. 1 2 3 4 5-stepped wave, like it's a stepped kind of staircase wave in this line to line voltage. And if you calculate the RMS of the fundamental, it will be equal to like 0.67 of the VDC in case of this 120-degree conduction mode. So you can see here that the devices are conducting for a smaller duration, like for a 120-degree. But what is happening, like the RMS is less in fundamental of the RMS is less in case of the 120-degree as compared to the 180-degree, where we had like VAB RMS equal to 0.78 times VDC, and here we got it was like equal to 78%. Here we are getting 67% only. Like you can do the analysis that has already been done during the course, like you can go through that. This was about this 120-degree conduction move. So now we'll be like moving towards the pulse width modulation. Now the first thing we want to discuss is why we will go for the pulse width modulation. If you are like able to like switch once pulse width is like will be generating a n number of pulses in one time period, and first we want to see why would we be going to like using the pulse width modulation. So why we need this pulse modulation is because like if you what we you saw in the previous, like we were able to generate these kind of waveforms, and if you do the Fourier analysis of this, you would see we will be having the lower harmonics here, like third, fifth, seventh, and what we want to have, and these harmonics, to eliminate these harmonics we'll be needing high value of filters like inductors or capacitors. In order to push these harmonics to higher frequencies, we do this pulse width modulation. I'll show you here, like this is our conventional this H bridge what we saw here, and we were able to generate this square wave kind of a waveform if we go for 180-degree conduction mode. And that means like well, we are able to have this one pulse of a positive voltage and one negative, like generating a square wave in a one switching cycle. But if we will be doing the Fourier analysis of this, you will be seeing we will be having the lower harmonics in this wave. Now if we could somehow like see if we could decrease the width of this waveform, let us say like we have a zero interval for some time, and I am only switching on like S1 and S2 for 2D amount of time, like 2D is some theta, 2D is some, sorry, it is here like 2D degrees, 2D degrees. So you can see here like when we'll be able to get VDC when S1 is S2 is on, and if you want to have this 0 voltage, I need to turn either S1 and S4, like no, S1 and S3 or S4 and S2. If I switch on S4 and S2, like we'll be having a 0 voltage, and if I be switching S1 and S3, still will be having 0 voltage. Now if you want to have this negative VDC, I'll be switching on this S3 and S4, and in a similar fashion here I'll be switching S1 and S3 to achieve this 0 voltage. If we can do this Fourier analysis of this, you can see that this, you can see like the fundamental, I have like what has been done here, the for the nth harmonic, the amplitude of the nth harmonic, it has been normalized with respect to the fundamental. Let us say like when we have the fundamental, like with, if you can see the variation of here, it is normalized from 0 to pi. If we have like a pi degree wavelength, the fundamental will increase, but you can see at the pi we have the other harmonic at the peak as well. You can see the third, fifth, seventh are also having like some magnitude, and it will be the peak magnitude of these harmonics. However, if I am able to reduce this conduction period by some amount, let us say for take the example of this third harmonic, if I'll take, you can see the amplitude of this third harmonic is coming out to 0 at some point, which is at 120 degree here, that is 2 pi by 3, 120 degree. If I have this 2D equal to 120 degree, I will be able to eliminate this third harmonic. You can see if my this width is 120 degree, I won't be having any third harmonic in this way. Similarly, for different like pulse widths, we will be able to eliminate different waveform, different harmonics. So we saw here, like by changing the like the duration of this wave, conduction duration of this wave, we can eliminate some harmonics, and certainly if you can see at like some of this pulse widths, you can see like beyond this certain point, like we can have the amplitude of these harmonics can also be reduced. So the idea is that like we want to vary the amplitude of this wave in order to reduce the harmonics in our waveform. So we go for different modulation techniques. You can see here like this is a single pulse width modulation, the basic that we saw here. Here what is being done, how the pulses we do is, we have a carrier waveform, that is this sort of a triangular waveform that will be moving, and we have this reference waveform or modulating waveform. And the logic is in such a way, when this VR is greater than this carrier, we turn on this device. If we move this reference towards the peak of the carrier, we can have 180 degree conduction mode, because the carrier will be greater than this reference will be greater than this carrier for the whole time. Similarly for this negative, if you move it for like towards the negative peak, we can have this S4 and S3 turned on for the whole 180 degree conduction period. As we lower this reference, like we can only get we'll only be turning on the device when this reference will be greater than this triangular wave. We'll be having our logic in such a way, then we can say that whenever this reference is greater than this carrier, we'll be turning on our devices. And now by simply like varying this VR between this 0 and the peak of this carrier, which usually is 1, we can like change the width of our pulses. And here we define a term like a modulation index, which will be equal to like peak of this reference wave divided by the peak of this carrier wave. This is known as the modulation index. So this was for the single PWM. Now we can see for the multiple PWM, the concept is same. Like for the positive, like we'll be doing whenever this is VR is greater than VC, will be turning on our devices. So we'll be having a like 0 to like we will be having a 0 here, VDC 0, VDC will be having a multiple pulses, like our waveform have be having multiple pulses in the positive and multiple pulses in the negative. Here this will be sort of a unipolar PWM. This is when we'll be having a constant, like we'll be getting a voltage waveform, we'll be having a constant amplitude of VDC for certain duration of time and 0 for this certain duration of time. Now we have one another modulation technique is sine, where we want to, here you can see like we discussed in some previous lectures like lecture 5 I think or 4, we saw that because of this multiple pulses, like we were able to have this voltage waveform that was closer to the sinusoid. But with this sine PWM, what we is done, like the idea is same, the logic is same. Whenever this VR is greater than the carrier, we turn on our devices, and when this is lower, we turn off our devices. Here you can see our like this modulation signal like is getting, like you can see is varied. The pulses of our voltage waveform will vary, like first it will be smaller, then it will gradually be larger, and it will be like larger, and then it will start to decrease. If you can see, it will be smaller, larger. Just a minute, I'll show you with the pointer. First it will be like this smaller, then it will gradually increase, and then it will gradually decrease. And in a similar fashion in the negative, it will be like smaller, then it will gradually increase, and it will be maximum at the peak and minimum. If you can see the average that we will be able to generate because of this, will be having will be closer to this sine wave. That is our objective, and because of that we'll be having the like lower harmonics distortion in this kind of like modulation. So what we got from here, like with the increased number of pulses, we'll be having that reduction in the lower order harmonics. So more the pulses, it is better, but there is also like we have to balance out the things, because with more number of these pulses, will be like switching our devices n number of times, like more number of times, and which can increase our switching losses. So we have to see an optimum point, like where we can have the more number of pulses, where our switching loss will be optimized, and our like THD will also be better. So now we will be like I'll be discussing about the multi-level inverters. So up till now we saw like we are able to have like this two level sort of a thing. If you can see, what we wanted to have is sort of a generate an AC voltage, and we know like the best AC voltage like we could generate is a sinusoidal that is available to our AC grid. So the simplest that we were able to generate is this like see a Cauchy square wave, where we have two levels, VDC 0 and minus VDC. And if you can see, the fundamental of this will be of this voltage waveform will be a sinusoidal waveform, which will be in phase in this with this. But you can see the instantaneous error between this sinusoid and this like Cauchy square wave is very high. Like there is a like much more difference between the values of the square wave and the fundamental. Like it is not the accurate approximation of this sine wave, you can see. Now if I am able to generate more number of like steps, you can see here I have like 1 step, 2 step, 3 step. You can see in here like the instantaneous error is decreased, and also if you can see this waveform, like this stepped kind of a waveform, it is closer to the sine wave. If you can see, more the number of steps, more closer it will be towards the sine wave, lesser will be the harmonics in it and harmonic distortion. If you can see like this, if you can see, if you have like more number of like 5 steps, it will be more closer to this sine. If you have 7, 11, like some of the steps, we can have like it can be closer to the sine wave. That is the idea of this multi-level inverters. We want to have the more number of levels so that we can generate a waveform that is closer to the sine wave. But this is not as simple. Like we can generate a number of like levels, but what happens with the increase in levels, the complexity with the topology increases. So that is here. So we are able to see first, like we had this topology, and earlier like we saw, and due to this, when this as top device is turned on, we can get a VDC voltage, and when this bottom device is on, we can get 0 voltage. So due to this, we are able to generate two levels only, like 0 and VDC. Now we'll see a topology by which we will be able to generate the 3 levels. If you can see, like VDC, I have connected like this two capacitors in series with like in parallel with this input DC, so that if you can see, if they are similar, we can have a plus VDC. We can like divide this into like VDC by 2 here. So here we can get, like, if you can see here, when this device is only on, I can get VAN will be equal to VDC. When this bottom device is on, then VAN will be equal to 0. And when this middle device is on, middle switch is on, then my VAN will be connected to this VDC by 2 terminal, and VAN will be equal to VDC by 2. So here we are able to generate like 3 levels: 0, VDC by 2 and VDC. So like I discussed, like the multi-level inverters, the advantages what we are getting because of this multi-level inverters is because with the increase in levels, we are like more closer to the sinusoid, and therefore our harmonics in the waveform will get reduced, because like our waveform, more the number of the states, it will be closer to the sinusoid. And in a similar way, like now you can see that these some of the switches will have to like block, like will be have to like going from 0 to VDC by 2, and they will have lesser switch stress, and this we have to, this will differ from topology to topology. And one another thing is, like, now when we are having n number of levels to go from 0 to peak, that is divided between the levels, you can see that the change in the levels will be now less. Instead of going to like 0 to VDC, we are going from 0 to VDC by 2. So we can say dV by dt is less between these levels, and which is also beneficial in terms of like these devices and all. But these are where the advantages in kind of this multi-level thing with the improvement in the harmonics and all. What the drawbacks we are having is, like, we require more number of the components. Like here you saw, instead of like 2 switches, we'll be requiring the 3 here. We'll be seeing some of the topologies where we have the different like switches. And with the increase in switches and increasing number of levels, I had already told, the complexity will also increase. So we'll be seeing some of the multi-level topologies. Is like the first one we'll see is this diode clamped. This is known as the diode clamped uh, converter. So here what we have is we are having the four switches S1, S2, S3, S4, and midpoint of S1 2 is connected like in the diode in this way, and diode 2, and where they are connected to the midpoint of these two capacitors. The voltage across these two capacitors will be equal to VDC by 2. So now we'll be discussing how we will be able to get these three levels of this voltage. So you can see, like, first we want to have like VA, if this is VA point, and let this be an N point. So if we want to have this zero voltage, let us say we are having, first we'll be discussing about this zero voltage. So if my S3 and S4 is on, we can say like A point will be connected to this N point, like I'll be getting this zero voltage. So when S3 and S4 is on, I'll be getting this zero voltage. Got it? Now we got this zero level by switching on this S3 and S4. Now I wanted to have this VDC voltage. How will I get that VDC? If I be switching on this S1 and S2, you can see this A point will be connected to this positive rail, and N point is here. We'll be getting this VDC voltage if S1 and S2 is turned on. Now these are quite simple, like you see this S1 and S2 are turned on, we get a VDC, S3 and S2 get 0. Now we'll see how we can get this VDC by 2 voltage. Now you can see here that if I switch on this S2 and S3 are switched on, then this A point is connected to, if you can see this midpoint, we'll be seeing this. How? So we can have, like, if you can see here, we can have the current direction in here can be in two ways, like it can be in positive way or negative here. If my current is positive here, then the current will flow through D1, then D1 and S2 will be conducting here, and my voltage, this A point will come to this midpoint, and my voltage will be equal to VAN will be equal to VDC by 2. And now if my current is negative here, then it will flow through, conducting path will be through S3 and D2, and here this path it will take, and it will be equal to minus VDC by it will be equal to VDC by 2, not minus VDC by 2, VDC by 2 if it is negative current. So during the positive current, D1 and S2 will conduct, and during the negative, D2 and S3 conduct. So because of due to this circuitry, we were able to generate three levels: 0, VDC by 2, and VDC. But here you saw that in order to generate three levels, we need to have like two more switches, two diodes, and two capacitors are to be needed. Like, this increases the complexity a lot in these topologies, but what we get is an improvement in the harmonics, like our harmonics are reduced in this topology. And another topology here is like what we call is a flying capacitor. Here you can see, instead of these two diodes here that is connected to the midpoint, we have an additional capacitor here. And in this topology, like the capacitors and like modulation is done in such a way, like each of the voltage across each capacitor is VDC by 2 is same. So if we want to have this zero voltage here also, we'll be turning on S3 and S4. Now if we want to have VDC voltage in the similar manner to the diode clamped one, we will be switching on S1 and S2. Now if we want to have VDC by 2, what we'll be doing, we'll be turning on this S2 and S3. So when S2 and S3 will be turned on, you can see no, sorry, if we want to have this VDC by 2 voltage, I'll be turning on this S1 and S3. or S2 or S4. Let us first see S1 and S3. When S1 and S3 are turned on, you can see tracing this path from here, the current will flow in this direction through S1, then through this flying capacitor, then through S3 and through the load VAN. And you can see if we use the KVL here, we have this VDC by 2, VDC by 2, that will be equal to VDC, and it will subtract, then this will be minus VDC by 2, and what we will be getting at VAN is minus VDC, is what we will be getting at VAN is VDC by 2. And when this is when the current is in this direction, and S1 and S3. Similarly, in another fashion, we can turn on S2 and S4. You can see then it will be like in this way. You can see when this is charged to VDC by 2, a point will be connected to VDC and n point will be connected to this, and VAN will be equal to plus VDC by 2. So here, in order to get VDC by 2, we have like two options, either switch S1 and S3 or switch S1, S2 and S4. So here we were able to get these three levels, 0, VDC by 2 and VDC, by switching on these devices S1, S2, S3 and S4 in this manner as has been shown in this table. You can see as compared to the diode bridge, here we have lesser devices, like two less diodes, but here we have one capacitor, etc. That is a trade-off we have to see. There have been maybe different applications where we'll be using different topologies. I'll move forward. One another inverter topology that has been taught is like the Z source inverter. You can see we have a, if you can take a look at this side, we can say that this is a three-phase inverter here, and between this and source there is an impedance network that is connected. Since this impedance is connected here, that is represented by Z, we can say that this is a VSI inverter between Z source inverter, because like Z is an impedance, and due to this we'll see we'll be getting it will has like additional functionalities as compared to this voltage source and current source. Coming to this, like we saw, we can have like different modes here. When this is normal state is, we can resemble this like by some load through current is flowing here, and we can represent this side as a current source, and VIN is the input voltage, like VIN is the voltage here, VI. This is the normal state when this will be on. And you can see compared to this VSI, we saw like we couldn't short we cannot turn S1 and S4 simultaneously in VSI, because like then source would have been shorted. But here we can S1 and S4 because we have some impedance, and the current will flow through it. That I'll be showing, that will be the shoot through state that I'll be discussing after this normal state. This is the normal state where we'll be having an inverter, like this is a load current here. You can see, since this is a symmetric, like if you can use a KVL in one of these loops, you can see that VL voltage here will be equal to VDC minus VC, if you can see this V1 loop. And similarly, if you can apply the KVL in this loop, you can see this VI will be equal to VC minus VL. And if you can substitute this VL here, we can see VI will be equal to twice VC minus VDC. This was the normal state. Now another state is shoot through state, where we have like S1 and S4 will be shorted. So when S1 and S4 will be shorted, there will be no current through the load. And since when there is no current through the load and our source there will be no current from the source, source will also be disconnected. What will happen? It will inductor and capacitor current will flow in this loop. What will happen here is VL will be equal to VC. VL will be equal to VC, and you can see as this VI is shorted, VI will be equal to 0. That is the shoot through state. You can go into the detail of this. You can see that have been taught in during the lectures. So we are able to see, like in the normal state VL this and VI was about to came out by this equation, and this was in the shoot through state. And if we apply that like volt second balance for the inductor, we have like VDC by V for the T1 interval, and VL will be equal to VC for T0, and here we achieved like VC will be equal to by this equation. Also, like we can like calculate the VI peak. VI was this Vi is this voltage, and we can calculate the peak of this. The peak of this will be equal to, since here Vi is equal to 0, and peak will be calculated from this, and if we put Vc equal to this, then minus Vdc, it will come out as this equation. And you can see this factor here is a boosting factor, and we simply denoted by B. You can see, because it will be equal to T divided by T1 minus T0. Since T is the whole duration of time, and T1 and T0 are less than will be always be less than T, so this factor will always be greater than 1. So here what we saw is, here in this Z source inverter we can get Vi which will be greater than like VDC. We can have a boost state here. That will be in the like three-phase inverter. What we had by equation, VAC will be equal to M V in by 2, M VDC by 2, or V in by 2. Here that VSI is like a buck converter, and it will always be less than. But here in this Z source we have a MB VDC by 2. Like here V in be equal to B VDC by 2. So here output voltage is increased by a factor of B, which is greater than factor. So here we can get a voltage higher than that of a VSI, but we need we have some impedance that need to be connected between this source and this inverter. That was about this what had been taught in this course. It was like a a number of topics were discussed, and it took some time. Like these were very important concepts that need to be understood. So this is for that revision part. Now we'll be moving forward towards the problem solving session for this. So here is our first problem. What is being told here is a single phase half bridge inverter is feeding power into a load of resistance. So we have a single phase half bridge inverter and is feeding a power into load is resistive, that is 10 ohm. So DC input to the inverter is like 400 volts. So what we have to determine is what is the power delivered to the load. So first we will see how the half bridge inverter looks like. So we have a VDC, we split it by, like we have two capacitors, and then we have this one leg of an H bridge here. And what we do is we connected load between this point and this point. So when this S1 is turned on, like we can have a plus VDC voltage, VAO is plus VDC. When S2 is on, VAO is minus VDC. You can see negative voltage will come here and positive will be here. It will be like minus VDC. So what is being taught is, we know when we have a like this resistive network, in case of a resistive load, the load current will follow the load voltage. Since our load voltage is VAO is square wave, so our current will also look like a square wave here. You can see here. So we saw here VO is VDC by 2, and now VO is VDC by 2. Peak of this VAO phase voltage is VDC by 2, which will be equal to 400 divided by 2. That will be come out to equal to 200 volts. Now we know VO peak. We know, now we can calculate the peak of the this output current. That will be equal to simply this voltage divided by the resistance, that is equal to the 20 ampere. That will come out to be equal to 20 ampere. Now if we know voltage and if we know the current, we can calculate the power, DC power, that is equal to V into I. Simply that will equal to 200 into 20, that will come out to be equal to 4 kilowatt or 4000 watts. So you can see that the D option is correct to the first question. It will be equal to 4000 watts. Now coming to the second question. Second question is, find the conduction time of the diodes if the SCRs are fired at 0 and T by 2 respectively in the single phase half bridge inverter with the R load. We saw the single phase half bridge inverter previously, like we'll be going. Can anyone answer this like A, B, C, D, like 0, T by 2, 2 by T, or insufficient data? Can anyone answer? Like take a guess, then we'll be going. There is a one answer is like someone has told A. Anyone else? Rajeshri, you can answer, or you can type whatever way you like. You can unmute or say, or you can type. So if anyone else isn't like guessing, like I will be moving, will be seeing. So here we saw the this is the half bridge single phase inverter like we saw, but here what is being given is we have a diodes as well, like we have with the devices SCR, these we know, and we have like this anti-parallel diode connecting with it. And we saw like, but it is also given that this load is resistive. And if you can see the previous, we saw when the load is resistive we have a positive voltage and the current will have the same direction as that of voltage. When you have a negative voltage, the current will have the same direction. So similar, on the similar basis, if you see, when this device is turned on, we have a plus VDC and the current will flow in this direction. AO is positive. You get it? That this is the positive direction of the current. And you know, when we turn on this device, the voltage here will be equal to this endpoint will be, this will be minus VDC, and the current at that moment will be negative, that will be conducted through this SCR. So you saw, like in case of a resistive load, at no point of time that these diodes conduct. So the whole current is like in the positive half is conducted by this top SCR, and during this negative half it is conducted by this bottom SCR. So what we can conclude from that is that, like for this resistive load, no diodes will conduct. So the answer to this question is like A for 0 time. So this is the question 3. If any of you wants to try it, you can try it. Like we will be taking like a 5 minutes break. We'll be joining at 8:25 back. So we can move forward with this third question. The question is like, the single phase half bridge inverter has a resistive load of 2.4 ohms and the DC output and the DC input voltage is 48 volt. We have an input of 48 volts and the load is 2.4. What we have to calculate is find the average value of the average supply current. So here what is given to us is input voltage is given to us and the load is given. So you can see we have a single phase half bridge inverter like we saw. If we like turn on S1 we get a VDC by 2 voltage, and if I turn on S2 I get a minus VDC by 2 voltage. And since this what is given here is the load is resistive, so the current will be in phase with the voltage. So the current will be have the same shape as this voltage and it will have some peak value that will be equal to VA peak divided by R. So since the VDC is given to us, and what we also know is if we consider this system as a lossless system, that we don't have any passivity or what we can say parasitics of these components, that means these components all are lossless and whatever is the input power will be at the output. So if we are able to calculate the output power and equate that with the input power, because we have the V input, we can get the input current. So it's simple, like to calculate the output power, if we know the output voltage we can calculate the output current, that will be peak of the output voltage divided by dr. So what is done here. So P will be equal to VAO, that will be equal to VDC by 2 into IO, that will be equal to VDC by 2 divided by R. So VDC by 2 is 48 divided by 2, 24 volts, and I will be equal to 24 divided by 2.4, that will come out to be 10, that is equal to 240 watts. So we know that the power is like output power is 240 watts, and if we see that this system is a lossless system and P in equal to P out, we can say that IS is equal to 240 divided by 48, that it will come out to be 5 amperes. Like it was quite simple, like what we had only to understand the approach to solve this question. So you can see here this the correct option is A, that is 5 amps. So the other question is, what will be the shape of the output current waveform of a single phase full bridge inverter on RL load? We have a sine wave, a square wave, a triangular wave, a constant DC. Can anyone answer? Any guesses? No. One is saying like the sine wave. Any other guesses? So we'll see. We have a first, like we saw for this single phase half wave inverter or full phase, you can see whenever we have a resistive load, the current will follow the shape of the voltage. When the voltage is positive, current will be positive with some amplitude that will depend upon the resistance or load, that will be equal to VAB peak divided by R. Now if we have a purely inductive load, that means we have VDC and I will be equal to, like it will be of integral of that, we know VL is equal to LDI by dt, and if we integrate V, then we can get the current. So it will be like a triangular wave if we are having a pure purely inductive. So now if we have an RL load, so what would happen, like it will during this positive half, like it will charge to some point, and when this negative voltage is impressed, it will start to discharge. So you can see it is somewhat triangular in shape but not exactly triangular. And you can say more the value of L, more will be like this will be closer to the triangular, and lesser the value of L, it will be closer to the R, and this whole current waveform will try to be closer to the square wave. Like more the L, it will be more closer to the triangular, and more the R and lesser the L, it will be closer to this square wave as in the first part. So when the question is asked, what we are assuming is that it is highly inductive load. When the inductance is very high, we can assume it is at an inductive, and we can assume that this current is closer to the triangular or as a triangular current waveform. So when we say this, then the shape of the current output current waveform will be closer to a triangular wave. That is, this option C is correct for this question. Question number 5. In a three-phase bridge inverter, each step consists of how many degrees? Like the options are 30 degree, 60 degree, 90 degree, and will depend upon the firing angle. Like we saw in the three-phase inverter, like now we have to, can anyone guess what will be the value of this each step? One option is like we will see. We saw this, if you can see, we have a three-phase inductor. Let us consider it in a 180 degree conduction mode. Since the mode is not giving, we can take it as this 180 degree conduction mode. So if we can see this, we see that S1 will be conducting for 180 degree and S4 will be conducting for 180, and for leg B it will be shifted from 120 degree, and if you see 120 degree, and it will be conduct for 180 degree, and C will be further shifted from 120 and 240 from the A, this. So here if you see we were able to see the line voltage VAB was a quasi square waveform. When S1 and S6 is on, here when S1 and S6 is on, VAB was equal to like VDC, and here when S1 and S3 is on, then VAB was equal to like 0. So the line voltage here was equal to like a quasi square wave. Now we wanted to have the phase voltage VAO we wanted to generate. So like if we have like VAO will be equal to like VAN minus VON. If we have this voltage, we can have this voltage waveform, and if you can see for this, if you can do the calculation of this waveform like has been done in the subsequent way like classes, you can see we'll be getting it like this waveform. Like during this 60 degree of conduction, we'll be getting the three-step waveform here, and it will be each step will be for the 60 degree. Like for this it will be 2 VDC by 3. If you can see, like when S1 and here S1 S6 is on and S3 is on, S1 S6 and S5 is on, S1 and S5 is on, and S6 is on. You can see, if you can make a here, if you can like draw the circuit, the A point will be connected to this, and then we have like VO point here, then it will be like this, and here we will be connected here. So we can, here we will be getting a 2 VDC by 3 voltage. If you can like solve this like this, here there will be one resistance, here there will be one, here there will be one. So what we see here is we can get like overall in the one we'll be getting the VAO. It will be a this staircase type of a thing where we have VDC to VDC by 3, and each of the like step is for 60 degree. That's why we call this phase voltage a 6-step wave as well. You can see that each of the step will be conducting for the 60 degree of the time. So with the different switching state, it will be a 6-step, and lower phase voltage will be having the 6 steps, like 1 step, 2, 3, 4, 5 and 6. You can see, and each step will be of like 60 degree. So the current correct option is B for this. Now the question number 6 is, in 180 degree mode VSI, how many devices conduct at a time? Can anyone answer this question? One is, now we'll be going through different, like there are different answers, like 2 and 3 will be going through this. Now firstly we'll be going through the 180 degree conduction mode. What we saw, as you can see, in 180 degree mode we talked about like each device will conduct for 180 degree. Like you can see here, S1 is conducting for 180 degree, and after that S4 is turning on for A, and B phase will be phase shifted from 120 degree, and it will also conduct from 180 degree, and so on. And similarly for phase C will be shifted from phase B by 120 and A from 240 degree, and it will be like also conduct for 180 degree. If you can take any interval here any interval like 60 degree interval, like if we can see, like we can divide it into 60 degree intervals. This is 160 degree, 160 degree, 160 degree, 160 degree, 160 degree, 160 degree. If you can see, like at each interval, like 3 devices are conducting, like here S1, S6 and S5 are conducting. Are you able to get it? So like previously we saw, the VAB will be equal to cos square, and our load phase voltage will be equal to 6-step waveform. So at each of this interval, 60 interval, like 3 devices are conducting, like S1 here, S6 and S5. So you can see in 180 degree conduction mode, 3 devices are conducting in each 60 degree. Now we come to 120 degree conduction mode. Here each of the devices conduct for 120 degree, here like S1, S4, and each leg is shifted from one another by 120 degree. If you can see, each, like here 60 degree, 60 degree period, we can see, like let us say from 0 to 60 we have S1 is turned on and S6 is turned on. Got it? So here you can see in like 120 degree conduction mode, only 2 devices are turned on in a period, and in 180 degree mode, like 3 devices are turned in a 60 degree duration period in one. So we can say that 180 degree mode, how many devices will conduct at a time, is 3 is the correct answer to this question. So one of you had thought about 2, that will be in the 120 degree conduction mode, not in 180 degree conduction mode. In 180 degree conduction mode, it will be 3 devices that will be conducting at a time. Coming to the problem 7. what we have here is a three-phase bridge inverter delivers power to a resistive load from a 450 volt DC source. We have like a source voltage is given to us, that is 450 volt DC, and also what is given is for a star connected load of 10 ohm per phase. Load phase is given. Determine the load power for 120-degree mode of operation. What we have to do is we have to calculate the load power for 120 degree. Like we saw earlier, for the three-phase inverter in the 120-degree conduction mode, in the 180-degree conduction mode, the waveform like we saw here, it will be conducting for like 120-degree on. And if you can see here, what we want to take this interval like 0 to 60-degree, we have S1 and S6 is on. When S1 and S6 is on, we have VAB equal to VDC. When S1 is and S6 is on, you can see here. When S1 and S6 is on, VAB will equal to VDC. But you can see here, VAO is the midpoint. We can say VAO will be equal to then VDC by 2, since this is symmetric and balanced. Like we can say VAO will be equal to VDC by 2, and VOB or BO, like we can have VDC by 2. Overall, it will be equal to VDC. So in this portion we got it VDC, VAO. Now we see in this portion when S1 and S2 are on, when S1 and S2 on, in the similar way we can get here VAC equal to VDC, but since this is symmetric and this is floating, like we can get this VA will be equal to VDC by 2. Now coming to like 120 to 180-degree mode period, we have S3 and S2 on. We have S3 and S2 on. At that moment you can see VAO is not connected at all. We have a voltage that is equal to BC equal to VDC. VAO is not connected at all. There will be no current through VAO. That will be, this means that the voltage across it is V0. So we got the voltage waveform of the phase voltage, load phase voltage VAO is a quasi square wave in case of a 120-degree conduction mode. We saw like in the 180-degree conduction mode, line voltage was cos square. In 120-degree conduction mode, phase voltage is cos square wave. So the peak of this current will be equal to like VDC by 2 and R. We know that when the voltage is resistive, we can get the peak value of the R, like current will follow the same shape as this voltage, and the peak value will be like peak voltage divided by the resistance. And also like RMS is given by this equation, and the derivation of this you can see in the detail during in the course lectures, and it is given by like root 2 by 3 into VDC by 2 R ka whole square. Like this is the peak value of the current due to this resistive nature. Like this will be the peak voltage divided by R is the peak current. Like 2 by 3 is because like it's a 120, it conducts for 120-degree. So when we calculate this, if you want to calculate now the power will be equal to, we know like it is a three phase, it will be equal to 3 into I A ka RMS square into R. Like for one phase into 3, it will be equal to this 2 by 3 VDC by 2 R ka whole square into R. Now we know the value of the R, we know the value of the VDC. We have to just substitute the values here and we'll be getting the answer. Like this has been simplified. What if in the 180-degree mode? Like you can go through the lectures like and see what is in the similar way. In here, if we are having the 180-degree conduction mode, you will calculate the first, see how the phase voltage is there, and if this is that is like a 6-stepped waveform, our current will be same in that 6-step waveform, and then you have to calculate the RMS of that. you have to calculate the RMS of that. You can like integrate that, how you calculate the RMS 1 by pi by the square root integral of the current in each interval, and you can calculate the RMS of that. You can see if there is a derivation of that that has this equation given, and you can simply use that equation for that only. And when you are able to have this, like the current for RMS current for the single phase, and you can calculate the overall power for one phase and then three phase multiplied by 3, and that will give you the total power, and here it comes out to be equal to 10.125 kilowatt, and that is the answer to this question. 10.13 kilowatt, that is B. It is like for each of the question you have to approach it what is needed. If you have to calculate the power, you need to calculate the phase voltage, you need to calculate the current or RMS current to the phase voltage, and you can calculate all the other things. Question number 8. It is like the three phase inverter has a star connected load where R is this and L is given 5 ohm and 23 millihenry, and it is given that the inverter frequency is 60 Hz. The DC input voltage is 220 volts. Determine the RMS line voltage. So when it is not given like the mode of conduction, we usually take 180-degree conduction mode. So here you can see already we had like seen how the waveforms for the 180-degree conduction mode will look like. When the switches like this will be, the switches are switched for 180-degree, and for each leg they are like shifted from 120-degree in a balanced three-phase manner. So we can get the VAB voltage. What we have to calculate here is the determine RMS of the line voltage. So when we have to determine the RMS of the line voltage, we need the line voltage. So we will be able to, we know that in 180-degree conduction mode the line voltage is like this quasi square wave VAB, like we had discussed how this comes out to be like this. So all we have to do is now to calculate the RMS of this waveform. So we have to use the similar equation that we used here in previously, this 2 by 2 here, but this was a peak of the current. Here we have to use the peak of the voltage. This will be equal to like root 2 by 3 VDC whole square. That is 2 by 3, 220 is given, it's square, it will be come out to be 179.629 volt. That is like, if you know these equations, you can easily solve this question. Like this is like put the value and get the answer. If you don't, then you have to like calculate the RMS for each interval, then sum up and calculate the RMS for the whole period, one time period. Question number 9. In a sinusoidal pulse width modulation, the comparator output is high when, now we have is the sinusoidal pulse width modulation. We have to check when the comparator output is high. There are certain options that are given, that triangular wave is like has the magnitude higher than the sinusoidal wave. Sinusoidal wave has the higher magnitude than the triangular wave. Triangular wave has a equal to sinusoidal. Can you anybody answer this question? Like we had discussed in this, in the sinusoidal PWM. Triangular wave has the magnitude equal to the sinusoidal wave. So I think like we can straight away eliminate this option C, because like if you can see the triangular wave and will be equal to for a small portion of duration of the time, and the comparison will work. Like we can have like two logics here. One thing is we have a carrier and we have a reference, and here our reference is like a sinusoid modulating signal or a reference signal. And we can have two logics. We can say that our pulse comparator output will be high. Comparator will give us some pulse or output voltage high when this reference is higher than this trapezoid. That is logic number 2 here we have discussed, when this reference is greater than this comparator. This is how we will implement our logic, and this comparator we can implement by our op amps or some digitally in a digital mean. But mainly this logic is used when this reference wave is greater than this comparator wave. But if we can have our logic in other way as well, it is all up to us. We can have, like, when this comparator, we can say when this carrier wave, that's this C, is greater than this comparator, we can have our logic high. We can have this way as well. But mostly what we use is we say when this reference is greater than the like this carrier, we say that our comparator logic should be high. We can use both of the option, any of the options is correct, like 1 as well as 2, but mainly what we use is like logic 2. Whenever this reference is greater than the triangular, we say that our comparator is high or our logic is high. So we can say this option 2 is correct because this is mostly used. Option 1 can be correct as well if someone uses that logic, and we can achieve still switch then the devices accordingly and can achieve the operation as well. Now coming to the last question. Several equidistant pulses per half cycle are used in dash type of. Is it necessary? Just a minute. Is it necessary for to work comparator for high? That is what I said. It is not necessary. Like this is like the comparator high means like the comparison is happening, like we want to generate the pulse. No, comparator, it is like, see, we are having two things, like you are not we have two things. We want to like give the pulse to the switch, so we have the two things here. We have a triangular, we have this reference. So we have a comparator circuit where we have these two inputs, and we have logic in such a way that if my reference is greater than, then you give some high value. Let us say if we have a digital, it gives as 3 volts, that is given to the digital signal processing, or some volts. Let's for example 1 volt or something. So ultimately what we want is we want to turn on our devices. How we want to turn on device? We want to turn it on from here to here. So our logic will be such, when this will be greater than this reference, my comparator should give me some value high. Let us say it will keep 0. At that moment my switches won't have any pulses. When it will be 1 or some voltage, that 1 means high, or some voltage, it will that at that moment those switches will start conducting. That is what it means here. Now the logic is up to us. If we want to have operate, like we can have our logic comparator in a circuit in such a way, like we say when this carrier is greater than this reference, give us the high input or turn on the device. Or we can have it other way, but most commonly that is used, we have this logic VR is greater than reference. When is greater than this carrier, we say this we turn our comparator output as high. So moving to the last, several equidistant pulses per half cycle are used in dash type of modulation technique. Anyone? So multiples, most of them you are saying multiples. Let's see. So we have like different things, like we have first like the single PWM. We can write away like it is saying equidistant pulses, that means n number of pulses, but due to this single PWM we can generate only 1 pulse per this half cycle, so this is not correct. So in the multi PWM what we have a constant reference, and you can see if we have a logic that VR is higher than when VR is higher than VC, we have this pulse. You can see that each of these pulse will be of the same width, and it will be like equidistant from one another. When these will turn on, it will be have the turn on time will be same and turn off time will be same. But what will happen if we have a sinusoidal PWM? You can see the reference amplitude is getting varied. So the pulse widths will vary. We'll have the small pulse width of small value at the start, and at the peak value we'll be having pulse width of large value. Like that means here the like turn on and turn off time won't be same. So the only option that is correct, that we have the equidistant and pulses, it will be in the multiple PWM, multipulse PWM. So this option is correct for this. So this was it for today. Up to this question, like that is up for today. If anyone has any confusion, you can ask. And I think it is like 9. What is the advantage in Z source inverter over the other? Like we saw this VSI. By VSI is having only the buck, works in the buck mode. Like we saw it, we have VAC. Just a minute. We saw, like we know in a typical this VSI, we have VAC at the output will be equal to M into VDC by 2 or V input by 2. That this, if you can see this is kind of a buck operation. But in the Z source, when we do the analysis, we got some this term B, that will be equal to T divided by T1 minus T naught, and this T1 and T naught are will always be less than this T. That means this term will always be greater than 1. So here we get an additional thing when we when we like back substitute this, we'll be getting the B times VDC by 2. So we get a factor that is greater than 1. If you can see, we can have a greater amplitude of this VAC due to this Z source inverter as compared to the conventional. Higher gain you can achieve, or a boost function can be achieved due to this Z source inverter as compared to this simple VSI or inverter. Got it? You can go through the details of it in the lectures. Okay, if like sorry, if like there are not any other questions, we can close our session for today. Thank you everyone. Thank you.